So for B5, we are given two sets, S1 and S2, and we're told they're linearly independent. And we want to prove that under these conditions, that they're both subsets of the same vector space, that S1 and S2 are also linearly independent. So what we're going to do is we're going to start with a linear combination in S1, intersect S2. So we're going to consider A x1 plus b x2 plus let's do a1 x1 a2 x2 plus an xn, where ai is in C, or for all ai is in the field, whatever the field is, and xi is in S1 intersect S2. Well, this implies that for all I, xi is in S1, which implies that a1 x1 plus a2 x2 plus an xn is in, it is a linear combination of elements in S1. Therefore, A1 equals A2 equals 0, as S1 is linearly independent. So S1 intersect S2 must be linearly dependent or independent, as all linear combinations equaling 0 have only 0 coefficients. Or 0 scalars. Awesome. So now we're going to look at B6, and I went through B6, and we're just going to go through the steps. So first, what we're going to do is we define what our even set is. Okay, so it's the set of real valued functions such that f of x is equal to or f of x is a function such that f of minus x equals f of x, and f of x is some real valued function. So we start by showing non-empty. And to show non-empty, we let f of x equals 0, then f of minus x equals f of x. Thus, the even valued functions is non-empty. There exists a function in it. Then, because the real valued functions is a vector space, we're now going to look at to show that the even functions is a vector space. We just need to show that if we have two vectors in the even valued functions and C in the real numbers, then C v1 plus v2 is also an even valued function. So because v1 and v2 are even valued functions, v1 equals f of x such that f of minus x equals f of x, and v2 equals g of x such that g of minus x equals g of x. And then we consider c v1 plus v2. So c v1 plus v2 equals c f of x plus g of x, which equals c f of x plus g of x, cf plus g all of x. And now we want to show that cf plus g of x is an even valued function. So we consider cf plus g of minus x. And we apply our rule And then we step down with our rule for vector multiplication. And now what we have is we have f of minus x plus, or c times f of minus x plus g of x, which equals c of f of x, or c times f of x plus g of x by definition, which equals cf of x plus g of x, which equals our cf plus g all of x, which means that cf plus g of x, or our cv1 plus v2, is in fact an even real valued function. So the even real valued functions form a subspace. And once again, we have our last question. And here we're going to prove it's false by using a counterexample. We can see that a does not, the leading term cannot equal 0. And we're just going to let v be some polynomial with a 1 in front. So we can see here, there's a 1 in front, and c equaling 0, and v being the 0 polynomial. And we don't want it to be the 0 polynomial here. So let this be 1 and v be minus 1x. Then what we get is we get 1 plus minus 1x squared. And this is going to equal x plus 2. And now, as, or 0x squared plus x plus 2. And as 0 equals 0, this linear combination is not in our set of quadratic functions. So the set of quadratic functions is not a subspace, as this leading term is going to be 0, which doesn't satisfy our definition.